So what exactly is linear quantization? Linear quantization is where we have a set of values which can be used to represent the signal, and these values are uniformly spaced. So there's a fixed set of numbers, and the distance between every number is consistent. So once we've identified the number of reconstruction levels that we wish to apply to our signal, then we can choose a rule that will allow us to map the amplitude to a certain reconstruction level. Okay, so as we discussed previously, that will result in some degree of approximation and some introduction of error as well in certain circumstances. So there are several ways in which this mapping can be achieved. The optimal way is to map from the input value to the reconstruction level is to round the input value to the closest reconstruction level. So in the case of, for example, 23.45672, we can round that to 23.46 if that is a reconstruction level in fact. So we're losing some accuracy in terms of the original signal which was captured, but we're representing the signal data using a finite series of numbers. One other way to achieve a quantization is to truncate the input value and truncate it to the closest level that is smaller than it. Okay, so again we're rounding, but we're rounding down in this case. Another way is to apply sign magnitude truncation, and in this case we're mapping the input value to the closest level, again whose value is smaller than its absolute value. Taking into account the sign of the number. So to give some examples as to what these actually mean. So assume that we have a scenario where we've got 4 reconstruction levels, and the 4 reconstruction levels to which our continuous signal will be assigned, one of these numbers, is -3, -1, 1 and 3. So if we have an amplitude in our continuous signal that we wish to represent digitally, and it has an amplitude value of 2.9. This will be mapped to the level 3 if rounding is used. Okay, so it's mapped to that value which is closest to it. So that value is 3, the value is closest to it. It will be mapped to the level 1 if truncation is used. So 2.9 will be mapped to the level 1 if truncation is used. So it's rounding the number to the closest level which is smaller than it. And again, whenever sign magnitude truncation is used, it will be rounded to the level 1 again. By way of contrast, if we have an amplitude of -2.9 that we wish to represent using our reconstruction levels, the number will be mapped to -3 if we're using rounding, so it's mapped to that closest value to it. It will be mapped to the number -3 again in the case that truncation is used. Okay, so it's mapped to that number, the closest number which is smaller than it, and it will be mapped to the level -1 in the case that sign magnitude truncation is used. So the closest level whose value is smaller than its absolute value. So as we're using fewer quantization levels, so in that previous example we had 4 levels. As we use fewer quantization levels, there's a loss in terms of the spatial detail. So a loss in terms of that detail between the numbers which are being represented, between the different amplitudes which are being represented. We're losing some of the detail in the numbers by having to jump to a bigger number or a smaller number. So as fewer quantization levels are used, there's a loss in terms of the detail which is actually captured, and we end up with a more general reconstructed value. Furthermore, certain artifacts such as contouring begin to appear. So contouring is a situation where we introduce some distortion into our reconstructed signal. So contouring refers to when artificial boundaries in an image, for example, become visible, and this is due to abrupt intensity changes between different levels of grey, for example. So because we're losing that detail in terms of small differences between individual values, then this is represented as a large change in the actual reconstruction signal. So whenever we apply the uniform or the linear quantization, where we've got linear intervals between the reconstruction levels, images usually start to see false contours with 6 or fewer bits per pixel. Okay, so when we're using a lower amount of information to represent the original signal, we begin to introduce distortion into the reconstruction. In contrast to an image, whenever we're transmitting audio signals, we can also hear some distortion with about 8 bits per sample. Okay, so these figures depend on the particular data which is being communicated, whether it's an image or an audio signal, for example. So the uniform quantization, the linear approach, may not be appropriate for all types of data which is being communicated, and there are a range of ways in which quantization may be applied. So to contrast the linear, the uniform approach to quantization, there is the non-linear approach as well. So the non-linear approach, so it's natural to expect that the amount of distortion introduced depends on the quantizer, and so one can try to minimize the distortion by choosing a good quantizer. So a good quantizer could be one where there's a good range of values being used to represent the original signal. So we've got a good level of spatial detail, smaller gaps between the individual levels and ranges. So with a sensible choice of these quantization levels, we may be able to do better than blindly taking the levels uniformly spaced. So we may be able to apply some more intelligent approach to selecting the levels at which we want our signal to be represented, as opposed to just simply uniformly spacing them, where some of the very important detail might be lost. So as an example of a situation where it might be better to not use uniformly spaced intervals, if we have an image and it never takes on a certain range of grey levels, then there's no reason to waste quantization levels in this range of grey levels. So we don't need to waste the allocation of these levels for certain grey values which are never actually used in the signal. So with the non-linear, the non-uniform approach, we're using the levels to more efficiently and accurately represent the actual data which is being communicated. So we could perhaps represent an image more accurately if the quantization levels were instead used to more finely represent grey levels that appeared often in the image. So as opposed to having these large interval ranges, which may perhaps represent values that are not actually being communicated, we can use some of this level space instead to represent more finely, so with more detail, the grey levels that are actually appearing in the image. So one way in order to understand how this can be achieved is to look at a histogram of the intensity of values in the original signal. Okay, so we can plot the x-axis being the intensity level and the y-axis as a number of samples in the signal that take on that intensity level. I've got a figure here coming up which will show you what I mean. So if we know the distribution of our values which we want to communicate, then we can formulate an approach to select the optimal choice of levels. So those levels which allow us to more accurately represent the original information that we want to communicate. So for a special case where the histogram is flat, or otherwise known as where all the grey levels occur equally often, then the optimum quantizer turns out to be the uniform one. So because we need to represent the full range of values in relation to that data, then selecting those intervals at a uniform range, a uniform interval between each level, then that will turn out to be the most optimum approach in this situation. So once we've decided how we're going to quantize our data that's being communicated, we need to make sure that when the image is stored or the data that's being communicated is stored, it also needs to store the reconstruction level information so that the image can be displayed properly. So when it's encoded on one side of the network and then transmitted, it needs also to be decoded on the other side of the network. So we need to have these reconstruction levels available so that the image can be reconstructed accurately again. So this incurs overhead in association with the communication. It's important to choose the optimum approach for the data that's being communicated and to use the same quantization approach as well for each image, because there is this overhead in terms of the information needed to decode the images at the other side of the network. So we can choose quantization levels to work for a certain class of image that we would expect to encounter in an application. So if we know something about the images in advance, and we know that certain lighting levels may or may not be expected, then a non-uniform quantizer may be useful instead. Okay, so we can exploit the information that we know about the image or the data that's being communicated in order to decide the way in which it should be coded in preparation for its communication. Okay, so if we don't know anything about the images, so we don't know about the range of the values which are going to be communicated, then it may be most reasonable just to stick to the uniform quantizer. So this may not be the most efficient, but it will ensure that we can capture the necessary information that we need to send. Okay, so the compounding approach to quantization. The compounding law. So we have speech signals which are sampled typically 8,000 times per second. So assume that we employ linear quantization to map the amplitudes of the samples to the digital levels. So we're using a linear approach, a uniform approach. We're having equally spaced intervals between the reconstruction levels for our signal. So it's been observed that 12 bits per sample are needed for a very good quality speech, but we would like to lower the bit rate because if we're sampling and reconstructing at this rate, this will require up to 8 megabytes of storage. So how can we more efficiently record our signal so that it lowers the bit rate? Okay, and we can use the compounding law in order to achieve this. So assume a speech signal is normalized to the range of 1, so its samples lie between -1 and +1. And if we examine a typical speech signal, we'll see that we rarely use the extreme values. Okay, so those values at +1 or -1 are rarely actually used. So if we're using a linear quantization scheme, we assign as many reconstruction levels for the larger amplitudes as for the smaller amplitudes, which are more probable to occur. Okay, so we're assigning as many reconstruction levels for the larger amplitudes as for the smaller amplitudes, which are more probable to occur. So you can see that this isn't the most efficient way of digitizing our signal for transmission. Okay, so this is what we mean when we're saying that these values at +1 and -1 are less likely to occur in the signal. Okay, so there's information there that can be exploited in order to communicate the data more efficiently. So the A law and the mu law are so-called compounding schemes that are used in telephone networks. So we've got our compression and our expanding schemes that are actually used in telephone networks. Okay. So the overall objective of this approach is to remove the effects, the detrimental effects of a channel with a limited dynamic range. So we're restricting the range within which the signal may be communicated. So this compounding law, these A law and mu law, expand small values and they compress large values. Okay, so larger amplitudes are mapped into a smaller interval range, and our smaller amplitudes are mapped into a larger interval range. Okay, so when a signal goes through a compounder, small amplitudes are mapped into a larger interval, and the larger amplitudes are mapped into a smaller interval. So we'll see what this means in the next slide. So we're using more quantization levels for the values that originated from small amplitudes. So those values which are more likely to occur, we're using more quantization levels. So we're having a greater accuracy, a greater use of detail at those small amplitudes which are most likely to occur. Okay, so this scheme is equivalent to applying non-uniform quantization to the original signal, where smaller quantization levels are used for smaller values and the larger levels are used for larger values. Okay, so we're taking into account information regarding the distribution of the values which are being communicated, and we're using this to more effectively code the original data in a way which will support better reconstruction of the original signal. Okay, so we can see the principle of the compounding law in this figure, where we have our larger amplitudes are mapped into smaller intervals and our smaller amplitudes are mapped into larger intervals.